y'all. Continuing with some more electrodynamics. And what I'll do is move on to chapter 5. Next one's are chapter 5 assignments. And what we'll do is move into a more complicated thing, which is Laplace's equations. Definitely need to remind myself on how these work. So let's take a look at this. These are again our problems from Pollock and Stump. That textbook is an old textbook. We have two concentric spherical shells of radius R1 and R2 with potentials V1 and V2. So we have this and another one on the inside. Radius R1 and R2, potentials V1 and V2. We have R1, R2, and electric potential 1, electric potential 2. Find VR between the shells and verify the del squared V equals 0 explicitly. All right. So this squared V, it should be times dot product. If I remember right, I think I have to look this up. I remember the precise breakdown of that. I probably have it written down. Excuse me, when I did it last time. That is correct. So it ends up being that. So that ends up being partial y partial z dot product partial x with a full v partial y, because this potential is being distributed about the whole del symbol. Plus v. So v. The thing is, this needs to be in spherical coordinates. So the spherical del. Let me see if I can find I have it written down as the one with the V already added. Let me just find the default one. Perhaps let me share the book again. Mm, both of those there. Go. Convenient spot. There we go. Now I figured it'd be easier to find the default del in spherical coordinates in the book, but apparently not. This is the book here. This is the del with a function in Cartesian. I'll just search spherical. I'll just use the one that I have and revert back. Getting closer. All right, here we go. So this is chapter 2. It's like tables 3, 2.3, and 2.4. That's what I was looking for. So we have del spherical is defined as, oh crap, they still don't actually have what I was looking for. I was looking for the separate one. Well, we'll just have the full one written down there. So they just give us the full Laplacian, which is what it is. That's 1 over r squared, partial with respect to r squared, partial v, partial r, plus 1 over r squared sine theta, partial with respect to theta, sine theta, partial f, partial theta, plus 1 over r squared sine squared theta, partial squared f over partial psi squared. And f in this case is v. So we'll come back to getting that explicitly. But first you want to find the potential between the two shells. So we can actually utilize this equation called the Laplace's equation. I'll rewrite that. So the idea is that we can use this equation to get the flux and also the electrical potential that's going through that space. So whatever it is that's going through that space, we can use this equation. So what we want to do is um, observe the fact that we have two of these. So we can say the V at R1 theta equals the sum L equals 0 to infinity of ALRL plus BL over R. And this is actually going to be R1, R1, L plus 1, and PL cosine theta. It's going to be the potential 1, and then potential at R2 theta equals the sum L equals 0, infinity, AL R2 L plus BL over R2 L plus 1 L cosine theta will give us V2. And one thing we can note is that the potential will be constant at the boundaries. So at the boundaries at R1 and at R2, it'll be constant. So that there will be a continuous uh, transition between potentials between these two barriers, right? So looking over my notes from before, reminding myself as I go. Now I know that uh, one of these is applicable for distant, and one of these is applicable for within. So we could work this out. So if the radius is external to the volume in question, um, then you'll have an exponent on a very big number, and this will go to infinity. So if we're on the outside, it must be this one so that it can actually terminate. And on the inside, we have very small numbers. So if we use this one, it will go to infinity. So this one must be the one for internal. And I'll confirm that later, but that's the logic behind which coordinate will be A or A or B will be 0 when we apply the formula. Let me see if the solutions add any more detail. All right, so we have that. So another thing that comes into play is the Legendre polynomials and theta dependence. So this is the first one. And this actually means PO as a function of cosine theta equals 1. So that's not, this right here is not PO times cosine theta necessarily. It's a function in and of itself that involves cosine. So that's something odd to keep in mind that has to be looked out for. So this is P1 cosine theta and this is P2 cosine theta. And that's just what they equal. So this whole thing equals that. And though it's not clarified in the solutions, we need to have a solution that's not dependent upon theta. Looking at this, because we have a spherical symmetry, it doesn't matter which angle you're at. It's the same. It only changes per the radius. That must be why it's not theta dependent. And the only Legendre polynomial that's consistent no matter what the angle is going to be the first one here. So that's how we know we have to have L equals 0 for this to work. So let's see how this works when we put in L equals 0. Right? A0 plus 0. Okay, so that looks right. And then we have all right, so we have those two. So, and again, we have this worked out because we have two spherically symmetric uh, uh, shells, conducting shells. There's a potential between them. Each of them have two different potentials. And because there's no change according to the angle, no matter which angle you're at, the potential is the same. It only changes per radius. The only Legendre polynomial that has no theta dependence is the first one, because the one where L equals 1, it depends on theta because you have a cosine theta. The one where L equals 2, you have 3 cosine theta, 2 theta, so it has to be uh, L equals 0. So we'll just plug in for L equals 0, and we get those. So what we'll do here is solve for A naught and B naught. So I suppose since these have to have a continuity between them, there needs to be some point where they equate, where they match. And we need to solve both of these equations for A naught and B naught together. So let's take a look and see the best way to do that. So if I was to add these equations, let me check one thing real fast. All right, got that worked out. So what we'll do here is add these two. So if I add these two, I get 2 A naught plus B naught over R1 plus B naught over R2 equals V1 plus V2. So we have uh, 2 A naught equals R2 B naught plus R1 B naught over R1 R2 equals V1 plus V2. Two A naught equals V1 plus V2 times R1 R2 divided by R2 B naught plus R1 B naught. I'm not going to go ahead and just divide this by 2 right now. So now notice that they use subtraction. It does give us a value though. So why don't we do a subtraction one and see how that works as well. We can compare the two. So I subtract these. Let's see, so we can eliminate the the thing is though, B naught, different denominators. Let's see how this works. We want to have it in terms of only one or the other. I'll try subtraction first. So if we subtract these two, we have B naught over R1 minus B naught over R2 equals V1 minus V2. So then we have R2 B naught over R1 R2 minus R1 B naught over R1 R2 that equals V1 minus V2. So we can say that this is B naught R1 minus R2 over R1 R2 V1 equals V1 minus V2. So then we can bring that over and say B naught equals R1 R2 V1 minus V2 over R1 minus R2. It's the exact same thing they have, except they subtracted. I didn't make an error in my subtraction. right? And if I substitute that in for B naught, we'll try the left one and the right one. We'll see which one is what they used. So we have A naught plus R2 V1 minus V2 over R1 minus R2 equals V naught. To be V1. So then we have A naught equals V1 minus R2 V1 minus R2 V2 over R1 minus R2. And looks like we're going to combine the denominator and say this is V1 R1 minus V1 R2 over minus R2 V1 minus R2 V2 over R1 minus R2. And hopefully one of these cancels. Let's see. I think they do. So A naught equals let's see. Left off a one of the minuses here. Three ones and three R2s. And it looks like somehow they simplified this. In a way I can't see clearly at the moment. But I'll leave that there for now. All right. So we have our A naught, we have our B naught, and we know that V equals these. So all we have to do is plug those in, and we get what our potential is. Oops. A naught, wherever our V naught. So what that means is we have two conducting spheres, two conducting surfaces, and we want to get the potentials between the shells. And the key is we want the potentials here between these two shells. So in that case, we have to do a Laplace equation for each for R1, R2. Use the popular Legendre polynomial. In this case, since there's no theta dependence, the Legendre polynomial with no theta dependence is L equals 0. Solve that at both radiuses. And then use the sum and minus of each of these equations to solve for B naught and A naught. And then we could just plug those back into the equations we use with the Legendre polynomial. So easy enough process. Now the thing is, the next step is going to be pretty hard without this simplification here. I see that they did the subtraction to get B naught. Plugging in B naught, well, you know what I didn't do? I didn't try the other one. So let's try plugging B naught into the other one. That's what will make a difference. I'm going to use this one, and that'll be A naught equals R1 V2 over R1 minus R2. That equals V2. That's A naught plus. Hopefully I didn't make that mistake last time. So then we have A naught equals V2 R1 minus R2 minus R1 V1 minus V2 over R1 minus R2. We have V2 R1 minus V2 R2 minus V1 R1 plus V2 R1 is R2. But still doesn't simplify quite as neatly. End up getting 2 V2 R1 minus V2 R2 minus V1 R1 over R2. So actually to say we can still plug these into here. It's just this direct confirmation that this is going to equal 0 is going to be quite difficult. But we could always keep that in mind in the future, that the Laplacian of the potential should always equal 0. But that's one way to test that we have the proper potential and that the Laplacian equals 0. Let's move on to the next one. Consider a cube made of 6 conducting plates of size A by A. So we have and each side is A. It encloses the space. All right. So what we'll do, I'll take a break, and then I'll come back and start this problem. This looks to be a long one. I remember this one. So I'll take a break here and come back, and we'll start from there. See y'all in a bit. Barely Barry Jr. out till next time.